In 1738, Euler stated and proved that no cube plus 1, not even fractions, can produce a square, apart from one case, when the cube is 8. That is, 2 cubed plus 1 equals 3 squared is the only non-trivial solution. Euler gave an exquisite proof by infinite descent, with a genuine descent in every case and subcase, a rare feature since most arguments of this type combine contradiction with descent rather than relying almost purely on the latter. However, when consulting the original sources, one finds that the argument, unlike others in the same publication, is presented only in a sketch form. Several steps, therefore, require clarification in order to be fully understood. In particular, in the final steps of the more delicate descent cases, Euler reaches an expression of the same shape as the original and asserts that it's built from smaller numbers, thereby allowing the descent to continue. This crucial size comparison is stated without explicit justification, and making it precise is essential for full rigor. In this presentation, we complete Euler's descent entirely within his own framework. Euler begins assuming the problem in rational form. A cubed over b cubed plus 1 equals a square, with a and b positive integers and coprime. Multiplying through by b raised to the fourth converts it into an integer equation. Factoring the left-hand side shows that b times a plus b times a squared minus ab plus b squared is a perfect square. The next step is to examine coprimality relations among these three factors. Before considering the general case, Euler isolates the special situation in which the product of the first and second factor equals the third. A short algebraic check shows that this identity holds precisely when a equals to b. Substituting into the factor expression indeed produces a square, and substituting a equals to b back into the original rational equation recovers the non-trivial solution. 2 cubed plus 1 equals 3 squared. Euler then turns to the general coprimality structure of the factors. Since a and b are coprime, it follows that a and a plus b are also coprime. Likewise, b is coprime with a third factor, so b itself must be a perfect square. Furthermore, the third factor equals the square of a plus b minus 3ab, so the greatest common divisor of the second and third factor is either 3 or 1. Thus, the proof splits into two cases. Before proceeding, Euler sets a plus b equals c. With this substitution, bc times 3b squared minus 3bc plus c squared must be a perfect square. Case 1. Suppose the greatest common divisor of c and 3b squared minus 3bc plus c squared is 3. Write c as 3d. Substituting into the original expression gives 9bd times b squared minus 3bd plus 3d squared. Thus, if the original expression is a perfect square, then bd times b squared minus 3bd plus 3d squared must also be a perfect square. But this expression has exactly the same shape as the original one, now with a strictly smaller pair bd replacing bc. In other words, we are back at the starting point. The same problem reappears with smaller numbers. From here, it may fall again into case 1 or case 2, and the descent proceeds. Case 2. The greatest common divisor of c and the third factor is 1. Then b, c, and the third factor are all squares. Rearranging the third equation gives 3b times b minus c equals w minus c times w plus c. Thus, the prime factors of b must distribute between these two factors. So we can write w plus c equals m over n times b, where n divides b, with m and n positive integers and coprime. Thus, w equals m over n times b minus c. Substituting gives this expression. After expanding and simplifying, we get b squared times 3 minus m squared over n squared equals b times c times 3 minus 2m over n. And so after simplifying, we have b over c equals 3n squared minus 2mn over 3n squared minus m squared. Next, Euler states that numerator and denominator have greatest common divisor either 1 or 3. This follows from a simple divisibility argument. Any common divisor d should divide the difference, m times m minus 2n. We can rewrite the denominator as minus m minus 2n times m plus 2n minus n squared. Now, if d divides the left-hand side and m minus 2n, then it must divide n squared and hence n. But if d divides m minus 2n, then together with n being divisible by d, this would force d to divide m, contradicting the coprimality of m and n. Hence, d cannot divide m minus 2n. So d could only divide m. And since the denominator is 3n squared minus m squared, then d could only divide 3. Therefore, the only possible common divisors are 1 or 3, exactly as Euler asserts. Thus, case 2 splits into two subcases. Case 2, subcase 1. Assume 3 doesn't divide m. Then the numerator and denominator are coprime. Recalling that b and c are squares, we obtain u squared over v squared equals 3n squared minus 2mn over 3n squared minus m squared. So v squared equals 3n squared minus m squared. This implies that v squared plus m squared equals 3 times n squared. But a prime over form for k plus 3 dividing a sum of two squares must divide each square. So 3 must divide both v and m. Since 3 doesn't divide m by hypothesis, this sign choice is ruled out. Euler now multiplies both numerator and denominator by minus 1 and so analyzes the alternative sign choice. From m squared minus v squared equals m minus v times m plus v equals 3n squared, the prime factors of n must distribute between m minus v and m plus v. Thus, we may write m plus v equals p over q times n, where q divides n with p and q positive integers and coprime. Then m squared minus 3 times n squared equals the square of p over q times n minus m. Expanding and simplifying gives this expression. Dividing through by p over q times n squared yields m over n equals 3q squared plus p squared over 2pq. Since u squared equals 2mn minus 3n squared, we get this expression, and therefore u squared over n squared equals 3q squared minus 3pq plus p squared over pq. Since p and q are coprime, numerator and denominator have greatest common divisor 1 or 3. If the greatest common divisor is 1, both numerator and denominator must be perfect squares. If the greatest common divisor is 3, both are of the form 3k squared. Either way, it follows that pq times 3q squared minus 3pq plus p squared is a square. This expression has the same structural form as the original one, but composed of much smaller numbers. Here, Euler gives no clue, but he was probably pointing to the fact that q divides n and n divides p. Hence, we obtain a smaller solution of the same type, and a descent follows, provided that q is smaller than n and n is smaller than b. Since q divides n and n divides b, what we really have is q is equal or smaller than n, and n is equal or smaller than b. The cases q equals n smaller than b and q smaller than n equals to b clearly yield a strict decrease, so the descent proceeds without difficulty. What remains unaddressed in Euler's argument is the limiting possibility q equals n equals b. When constructing an infinite descent, it is common that a transform expression may reproduce the original equation in disguised form. so no genuine decrease occurs and the descent collapses. Therefore, this boundary case must be ruled out explicitly. Assume Q equals N equals B. From this previous equation, we obtain m squared minus 3n squared equals the square of p minus m. Hence, p times 2m minus p equals 3q. Since p and q are coprime, it follows p equals either 1 or 3. P equals 1, then 2m equals 3q squared plus 1. And if p equals 3, then 2m equals q squared plus 3. On the other hand, b equals n times 2m minus 3n. Substituting b equals n, we have b equals b times 2m minus 3b. Hence, 1 equals 2m minus 3b. And using b equals q, we obtain 2m equals 3q plus 1. Case p equals 1. Then 2m equals 3q squared plus 1, which equals 3q plus 1. Hence, 3q times q minus 1 equals 0. Thus, q equals 1 and m equals 2. Recall that the third factor equals the square of m over n times b minus c. Since q equals n equals b equals 1, we obtain 3 minus 3c plus c squared equals the square of m minus c. This simplifies to m times 2c minus m equals 3 times c minus 1. Substituting m equals 2 yields 4 times c minus 1 equals 3 times c minus 1, which is impossible since c is bigger than b, which equals 1, ruling out the case. Case p equals 3, then 2m equals q squared plus 3, which equals 3q plus 1. Factoring q squared minus 3q plus 2 equals 0 gives q minus 1 times q minus 2. When q equals 1, then m equals 2, leading to the impossibility already obtained above. When q equals 2, then m equals 7 over 2 is not an integer, also ruling out this case. Since the equality q equals n equals b leads to contradictions in all cases, strict inequality must hold. Q is smaller than n, which is smaller than b. Hence, the construction indeed produces a smaller positive solution, and Euler's descent is fully justified. Case 2, Subcase II. Assume 3 divides m. Write m equals 3k. Substituting and simplifying gives b over c equals n squared minus 2kn over n squared minus 3k squared, or 2kn minus n squared over 3k squared minus n squared. In this final form, numerator and denominator are coprime, hence each must be a perfect square. We can discard the second sign choice since 3k squared minus n squared cannot be a square. This would make 3 a sum of 2 squares. Thus, we proceed with the first sign choice, where both n squared minus 2kn and n squared minus 3k squared are perfect squares. Following the same reasoning applied for subcase 1, we deduce n squared minus 3k squared equals the square of n minus p over q times k, where q divides k with p and q positive integers and coprime. Expanding and simplifying yields 2kn times p over q equals k squared times 3q squared plus p squared over q squared. Hence, n over k equals 3q squared plus p squared over 2pq. Since b equals n squared minus 2kn, we obtain u squared over n squared equals p minus 3q times p minus q over 3q squared plus p squared. We could check common factors of numerator and denominator as done in subcase 1, but since the fraction is a perfect square, regardless of whether numerator and denominator are coprime or not, the product is always a square. Next, set p minus 3q equals r and p minus q equals s. Then p equals 3s minus r over 2 and q equals s minus r over 2. A direct computation verifies that 3q squared plus p squared equals r squared minus 3rs plus 3s squared. Therefore, r times s times r squared minus 3rs plus 3s squared is a square. This has the same structural form as the original one. Here, Euler asserted the new expression is smaller, meaning the absolute value of this new expression is smaller than the absolute value of the original expression, and therefore leading to a descent. While he did not provide a proof, fortunately, the required inequality can indeed be established entirely within Euler's own framework. From P equals 3s minus r over 2 and Q equals s minus r over 2, it follows R and S have the same parity. If both are even, we can factor out 2 raised to the 4th and obtain a smaller square, thus producing a descent. If both are odd, then they are coprime. Any common divisor would divide both the difference, s minus r, which equals 2q, and 3s minus r, which equals 2p. But this is impossible since p and q are coprime and r and s are odd. Hence, r and s are necessarily odd and coprime. Returning to this previous equation, we substitute p and q, yielding this other expression. We then expand and cancel n squared, and then divide through by k. Then multiply by the square of s minus r, expand, regroup, factor, simplify, and factor again, obtaining n minus 2k times r squared plus 3s squared equals 2 times 2n minus 3k times rs. Since r and s are coprime, it follows that s divides n minus 2k. Recall that b equals n times n minus 2k. As b and n are positive integers by construction, we obtain n minus 2k is bigger than 0. Hence, the absolute value of s is equal or smaller than n minus 2k, which is smaller than b, which is smaller than c. Similarly, using again the coprimality of r and s, we observe that the greatest common divisor of r and r squared plus 3s squared equals the greatest common divisor of r and 3. Hence, the greatest common divisor is either 1 or 3. Therefore, r divides 3 times n minus 2k. If the greatest common divisor of r and 3 is 3, write r as 3r sub 1. Then Euler's new expression equals 9 times another expression of the same form. So that second expression must also be a perfect square, given an immediate descent. If instead r and 3 are coprime, then r divides n minus 2k. Hence, the absolute value of r is equal or smaller than n minus 2k, which is smaller than b, which is smaller than c. In summary, in the remaining case, the absolute values of r and s are equal or smaller than n minus 2k, which is smaller than b, which is smaller than c. Thus, Euler's new expression is built from strictly smaller integers than the corresponding parameters b and c in the original expression. The descent is therefore genuine, and Euler's infinite descent argument is complete. That's all, folks. Thanks for watching. If you enjoyed this content, don't forget to give it a thumbs up, leave a comment with your thoughts or questions, and share it with anyone who might find it valuable. Your support means a lot.